As you can see from this opening slide, we're starting chapter 8 in the CPM book this week, and it's all about quadratic functions. So basically, we're going to be ending the year with quadratic functions and exponential functions. So you could look at this as the beginning of the end here. All right. For today, we're going to focus on section 811, which is an introduction to factoring quadratic expressions. Right, what I've done is created a slideshow, and we'll be using this slideshow to actually do the problems from this section. All right, so first of all, for the learning target, really it is learning what we mean by factoring and just having a look at some models of factoring. We'll also be reviewing a few things that we're going to need throughout this chapter. Okay, so let's take a look at this first example. We've been working on multiplying polynomials. So here's an example of a binomial times a binomial. So remember, when you do that, you want to distribute the 2x to both and the 3 to both, and then combine like terms. So when we distributed the 2x, we got 2x squared minus 12x. When we distributed the 3, we got the positive 3x and the negative 18. And then you combine like terms. So what we would say is 2x plus 3 times x minus 6 is equal to 2x squared minus 9x minus 18. This right here really explains the best I can about what factoring is. So I want you to think of factoring as polynomial division, or you could just think of factoring as division, period. We'll be learning how to take a quadratic equation like 2x squared minus 9x minus 18 and determine its factors. In this case, the two factors are 2x plus 3 and x minus 6, right? And we'll be using this to solve for variables and to solve some problems. But you can think about this as taking the answer and finding the problem. It's the same as mathematics, right? If I said, well, what is 2 times 9? You'd say 18. Then I would also say that a couple of factors of 18 are 2 and 9. Basically, it's division. All right, so we're going to learn a few ways to do that. In order to prepare for that, we need to review a few things. Okay, so the first thing I just want to run through is diamond problems. It's been a while since we've done these. So remember that at the top of the diamond is the product. At the bottom of the diamond is the sum. So what you're looking for in each of these are two factors of the top term that will give a sum of the bottom term. This becomes very useful to us when trying to factor quadratics. All right, so I'd love it if you just take a few minutes, try to figure out what x and y are in these problems, and then when you're ready, get the video going again. Okay, so here are our answers here. The x and y are interchangeable. It doesn't matter what they are. So you might have had the negative 8 here and the 10 here. That would be true of all of these. So I'd like you to just double check your answers. See if you got the same thing. The only one I want to talk about is this one here. As soon as you have a negative, all right, as your product, you automatically know that one of the terms has to be negative and the other one has to be positive. So that's why in this case, we wanted a product of negative 7x squared with a sum of negative 6x. So first thing I would do is think, well, what are some of the factors of 7, right? 1 and 7. I know the larger one has to be negative, so it would be negative 7x and positive 1x. All right. Hopefully that little reminder is all you needed. All right, let's go on to the next thing. Another thing we're going to be doing is looking at algebra tiles. I'd like you to think about algebra tiles as just a way to model what we're doing. Algebra tiles are not really what I would say are efficient, but I love them because they really show what's going on. So in problem 8.1, you're asked to take this picture and you're asked to find the area of this, which would end up being a quadratic written as a sum. And then you're asked to find the dimensions of it, which would be figuring out the area of this written as a product. All right, so again, I'd love to have you pause for a bit, see if you can figure out, well, what is the complete area inside, which would be combining like terms, and then what would be the dimensions of each side of the rectangle that would give you that area. When you're ready, go ahead and keep going with the video. Okay, so I've got my answer here. All right, so what I did is simplified as I went along. It might be a little easier to see over here on the right-hand side and maybe even here on the top what's going on, but I tend to write things on the left and the bottom. I always do double check both sides though. All right, so you can see like from here to here, that's going to be 4, very obvious here. And then from here to here is x, again, very obvious on this side. So x plus 4 would be our length here. And then the width, so this is y, again, it's more visible up here. This would be x and this would be 2. But again, you can see it down here too, y, x, and 2. So the dimensions of this rectangle are 4 plus x and y plus x plus 2. All right, well, really, we just factored a quadratic using algebra tiles. All right, so let's take a look at that. I didn't say before what this was as a sum, but you can see it's xy. I'm sorry, it's x squared plus xy plus 6 x's, 4 y's, and 8. So this is the area of that written as a sum. And then if we take the dimensions apart, we've got x plus 4 on one side, x plus y plus 2 on the other. You can see I wrote them in different orders. That's just because generally speaking, we write the x's first, then the y's, and then the constants. All right, but let's double check that. All right, let's multiply these two things together and see if we end up with this again. So I'm going to distribute the x to each of these, then I'm going to distribute the 4 and then combine like terms. All right, so when I distributed the x, I have x squared plus xy plus 2x. And then when I distribute the 4, I have plus 4x plus 4y plus 8. Then when I combine like terms, which the only thing I can combine here are the x's, when I did that, I got x squared plus xy plus 6x plus 4y plus 8. Right, so yeah, we factored the quadratic into its two factors. And then when we multiplied them together as a double check, sure enough, right, we got this answer. So we got our polynomial. This is a good picture of that. But what we're going to learn to do is how to do this type of thing without using algebra tiles. All right, another review we need to do is generic rectangles. Remember, we can't use algebra tiles when we're working with negatives. So again, all of this actually is dependent on the area model. So what we're going to do is find the area of each of these boxes in here, which will allow us to find the area of the whole. So I want you to use these generic rectangles to multiply these two binomials. All right, so if you got 18x squared here, negative 3x here, 12x here, and negative 2 here, then you did that correctly. And again, this is a good visual model of multiplying a binomial times a binomial. We have the same things here that we had in the smaller rectangle. So 18x squared, this is me distributing the 6x, and then 6x times 2 is positive 12x, so that's right here. Then I distributed the negative 1 and got negative 3x minus 2, and again, you can see where that shows up in the rectangle. Then when I combined like terms, it's 18x squared plus 9x minus 2. Right, we just needed to do a review of generic rectangles because these are also going to be coming up as we factor quadratics. All right, so that was problem 8.1. Here's some of the important information from problem 8.2, and that is the process of changing a sum to a product is called factoring. Okay, so for example, this quadratic is written as a sum. Right? If we say you need to factor it, then you need to write it as a product. So we're looking for its factors. All right, so right here, I just wanted to review the algebra tiles here. So I have built a rectangle with algebra tiles that matches this polynomial. So here's my 2x squared. My x is 1, 2, 3, 4, 5, 6, 7, and then I have 6 units. All right, well, then I can use that once I've built the rectangle to help me factor it. So I have x plus 2 on this side, 2x plus 3 on this side. We just factored that quadratic, right? And then I'm just going to say, let's take a look at the generic rectangle as a double check, right? So if I have x plus 2 on the left-hand side times 2x plus 3, does that really result in 2x squared plus 7x plus 6? And I think you can see by looking at it, it does. So 2x squared plus, if we combine like terms here, it would be 7x plus 6. Okay, so again, we're just doing an introduction today, but I'm hoping you can see how the generic rectangles and the algebra tiles kind of help us see what it is we're doing. Okay, now for problem 8.3, I want you to practice this. I want you to find the sum and the product for each of the following generic rectangles. So to find the sum, you would just combine like terms if you can, right? And then that would be, again, that would be the sum. And then to get the product, see if you can figure out what the dimensions are, right? I'm not going to give you very many hints on that today. We'll be talking about that a little bit later. But for now, just give that a shot. See if you can figure out the sum and the product for each. Combine like terms for the sum. Find the dimensions for the product. All right, just pause for a bit. Give it a try yourself, and then you can check your answers. Okay, so here are the answers for each. Okay, so you can see the sum for the first one, all we could combine was the 15x and the 2x. And the product on that one is 3x plus 1 on one side, 2x plus 5 on the other. So I would say 2x plus 5 here, then your 1 would have to be here, and this would be your 3x, right? Letter B, the sum is 5xy plus 15x minus 2y minus 6. You can't combine anything there, so that's why you have 4 terms in this polynomial. All right, and then it's 5x minus 2, right? So I would say your 5x here, negative 2 here, so then your y would have to be here and your positive 3 down here. Right, and then the last one, 12x squared plus 7x minus 12, right? And you could combine these two here, right? So to get your product, 4x minus 3, so I would say your negative 3 would be here, your 4x here, so 4x negative 3, then this would be your positive 3x and your positive 4 down here. Don't worry if you weren't able to get those. We'll be talking about some hints as we go along in this chapter about how to get those dimensions really quickly. We'll have a few different methods. All right, so problem 8.4, Casey starts to notice a pattern in the generic rectangles. Basically, she runs out of time, but she sees some patterns here. See if you can see what the pattern is. Right, I'm hoping you saw it. Okay, and the pattern is that the product of the diagonals is equal. So 15x times 2x is 30x squared, and 6x squared times 5 is also 30x squared. So this was rectangle A. Is it true for B and C? All right, well, let's take a look. So we've got 15x times negative 2y. So 15 times negative 2 is negative 30, so negative 30xy. And then 5xy times negative 6, all right, that's negative 30x. Yep, same. I hope you can see why we've been reviewing exponent rules here. We're going to be using them quite a bit. All right, what about this one here? So 12x squared times negative 12. So 12 times negative 12 is negative 144. So this would be negative 144x squared. And 16 times negative 9, that's also negative 144. And then we've got x times x. So yeah, both of the products here are negative 144x squared. So yes, it appears that this pattern always works. So problem 8.5 was just checking to see if that pattern works for all of them. All right, it appears that it does. We can't know for sure that it always does. That gets into something called deductive versus inductive logic. Inductive logic is looking at examples to see if you think it works. So this would be an example of inductive logic. We think it works. Deductive logic is when you prove that something always works. Later, we will prove this in a deductive manner. All right, so I'm giving you a little bit of an intro into geometry, which most of you will be taking next year, because you will be doing some geometric proofs using inductive and deductive logic. Again, this is just inductive. It doesn't prove it for all cases. So when using inductive logic, which uses examples, the best you can say is that it appears that this pattern works. All right, that is it for section 8.1.1. I just want you to fill out the questions on the Google Doc, hand that in, and you'll be all set for today. All right, nice work, everybody.